All right. Well, I first off want to thank Holden and thank you all for attending this webinar. I'm excited to be with you guys for the next hour. As Tracy mentioned, really going to be looking at the Greenheck rooftop ventilators and outside air equipment. I've been with the Doas group here for just over 3 years. Sounds like many of you are very familiar with our equipment. So we'll do a quick overview, just kind of give you a quick reminder of what we do, what applications we're serving, quick tonnage and airflow and cooling and heating options. And then I want to get into some more in-depth conversations about Doas, the industry, and this equipment. So we'll look at some efficiencies and cooling operations, some conversations around those topics, energy recovery, some differences between aluminum and polymer wheels. We'll look at some controls on this type of equipment. And then also at the end, we'll touch a little bit on, your traditional rooftop unit versus Doas and when you might want to make that change and some things to keep in mind when looking at the difference. So first off, with the Greenheck outdoor air equipment, we really provide packaged ventilation equipment that conditions and dehumidifies high percentages of outside air. And we'll touch on high percentage of outside air as we go through this. But typically looking at that 20 to 100% range is what we classify as high percentage outdoor air. So common applications that we're really serving with this type of equipment, a lot of education facilities, about 65% of Greenheck's Doas work goes to education facilities like classrooms, gymnasiums, auditoriums, things like that. I do a lot of corridor ventilation with Doas units, so hotels, multifamily establishments. Also get into healthcare and food service with this type of equipment as well. So anytime that you're really thinking about bringing in high percentages of outside air where we need to worry about comfort cooling, the occupants in the space to make sure that they are happy, they are comfortable, that's where you're going to want to apply units like the Greenheck Doas equipment. From an overall capacity standpoint with the RV and RVE, you're looking at 500 to 18,000 CFM. So wide range of CFMs there, anywhere from 3 up to 70 tons of package cooling with or without energy recovery. So obviously sliding the energy wheel upstream of all your cooling and heating and downsizing that accordingly. And then from heating and cooling options, so we do have the indirect gas furnace, electric heat, hot water coil. We have the air source heat pump from 5 up to 30 tons, if that is something that you see in your area at all. And then from cooling, obviously the heat pump does both heating and cooling. Package DX that we already touched on. Split DX with or without our remote condenser, which we will also touch on. The Greenheck provided remote condenser. And then chilled water coil. So those are the airflows, the tonnages, as well as the heating and cooling options that I want you to keep in mind as we're going through some of the overall topics related to the Doas market. Also wanted to bring up the newest model that rolled out most recently, the RV10, that really expanded our airflow and tonnage downwards. So really the RV10 now goes down to 500 CFM, providing that compact size and weight, keeping you all more competitive at that tonnage and airflow range. So that one is specifically 3 to 7 tons, up to 200 MBH of gas heat, has an electric heat option, and it does have the 208, 230, or 460 volt options as well. So can be 100% outside air, or as I mentioned, can have partial recirc. That 20 to 100% outdoor air is generally where you want to live with this type of equipment. Also did design that housing with vertical and horizontal connections to make it easier for installation purposes. So now I want to move maybe away from the RV, RVE specifically, and into some of the efficiencies and components that we do have on this housing that maybe you'll see on this housing in submittals, so that we can touch on why we offer what we do on this type of equipment. So first thing I really want to talk about is cooling efficiencies. And I want to compare what you might be used to or what you might see depending on certain situations in your submittals from Greenheck. So the first one is that Ieeer value, or that integrated energy efficiency ratio. So that is the part load condition that is tested to standard HRI 340, 360. And it's really looking at the MBH per kilowatt hour to determine the efficiency. So if you compare that to the ISMRE, if you've ever seen that, it is standard HRI 920. It stands for Integrated Seasonal Moisture Removal Efficiency. So generally, if you see that on our type of equipment in the submittal package, or you hear any of the Holden guys talk about it, that is going to be for a true Doas type system. So I'm gonna jump all the way to the bottom of this table. You see that ISMRE is used for Doas equipment versus that IEER, it's really indicative of that partial recirculation style unit. And if you look at the condenser entering air temps, pretty similar to the conditions that those units are actually tested of. But the biggest difference is going to be that evaporator entering air temp. So on the IEER side of things, those are always tested at 80-degree dry bulb, 67-degree wet bulb entering conditions. So there's no variation of when that air is entering that evaporator coil. It's always that 80, 67, regardless of what the actual outdoor air temp is. So yeah, the condenser is getting tested for those 95 degrees, 81.5 degrees, and so on conditions. But that evaporator is not seeing that variable conditions, which really indicates that there's going to be a high percentage of recirculation, and it's going to be pretty consistent temperatures across that evaporator coil. If you look at the ISMRE value and the evaporator entering air temps, now you see a wide range of conditions that HRI 920 is testing different dry bulbs and wet bulbs, whether it's hot and humid, whether it's pretty mediocre as far as conditions being part load, or you can see all the way at the bottom at condition D, it's 60-degree dry bulb. So it's not very warm out, but there's a really high wet bulb compared to the dry bulb. So it's a lot of humidity in the air that we still have to strip off moisture. And we are trying to determine how effective we are of dehumidifying that or removing that moisture. And that's why in this ISMRE value, the units are actually looking at pounds of moisture removed per kilowatt hour versus strictly MBH. So hopefully that makes sense. Again, I'm going to break it down on a psych chart so you can really paint that picture. But you see that the point in red, that is the ABCD, that is every condition, no matter what, that is the entering air temp into the evaporator. So it's going to be pretty consistent from a capacity standpoint and from an efficiency standpoint. When you look at the ISMRE, now you can see there is a whole wide range of conditions, and that really indicates that 100% outdoor air. So, you know, in the Georgia area, you can have days that are extremely hot, but maybe not as humid, or you can have days that are a little bit cooler, but they're going to have a high amount of moisture in the air, where in these applications where you're using this Doas type equipment, you're definitely going to want to make sure that we're stripping out moisture. And that is really the efficiency value that we're going to want to care about. So hopefully that makes some more sense as to why you will see ISMRE versus that IEER value in submittal packages.
So real quick, Jake, there is a question specific to that. Do any energy codes require ISMRE to be used in lieu of IEER? So
that's a really good question. And actually, they're still working on it, and it's going to continue to be adopted. But you can see ASHRAE 90.1 in this screenshot. Those are ISMRE ratings have already been adopted in 2013. I believe the last time I looked at the Georgia area, it was on the 2007 version of ASHRAE 90.1. So as it continues to upgrade the ASHRAE standards that you follow, you'll definitely see that requirement more and more for ISMRE. But I will say that the DOE is really trying to finalize as we get out to that 2022, 2023 timeframe where they're hiking overall minimum efficiencies. That's when they're going to start to enforce ISMRE for Doas equipment instead of just IEER. So while in theory you can still provide IEER for, you know, partial recirc and technically even 100% outdoor air units because the codes haven't fully adopted ISMRE, ISMRE really points a much better picture as to what you need to test for from an efficiency standpoint. But again, if you look at the 90.1 2013 version and beyond, there will be minimum efficiencies. And also for Doas equipment, we will put what the minimum efficiency is in 90.1 and then what our tested number is as well. So now I want to look at the compressor comparisons related again to cooling and efficiencies. So first one is going to be the digital scroll. And this is really loading and unloading based off of demand. And when I say loading and unloading, it is almost like a mechanical clutch in a vehicle. Where what digital scrolls actually do is they have a really good ability to modulate to capacity. So you still get that tight temperature control, but it's looking at a 15-second window. And that based on the capacity required, let's just say 50%, then it's going to load for 7.5 seconds and unload for 7.5 seconds based on that 50% capacity requirement. But when it loads and unloads, even when it's unloaded and not technically compressing, it's still rotating full speed and the motor's operating at full speed as well. So it's very inefficient from a part load condition. So when you get to those part load days, it's going to be unloaded a lot more than loaded, which means you're not compressing it, but you're still wasting a lot of energy. So inverter scrolls, now this capacity is really varying based on motor speed. See if I can play this video. I don't know if it's going to work, but basically what the VFD does is it's going to actually slow down that frequency. So if it's again 50%, we can slow down that motor to 50% instead of just loading and unloading that compressor. So you get really high part load efficiency values. And there's a number of other advantages, but it's about 20% higher in that, let's just say that Ieeer value compared to the digital scroll. Again, thinking about those part load conditions, not at full capacity, we want to make sure that we're turning down that motor speed to save energy. You also get this saving, but still having precise temperature and humidity control still has really good turn down with that as well. And then that third benefit you get is you get reduced sound levels. So I'm not sure if anybody's ever heard of digital scroll load and unload, but a lot of calls that we get from the service side of things, they ask if our compressor is broken, or they're calling to see what's wrong with it because they think that loading and unloading sound means something is happening. When in all reality, it is just a pretty obnoxious sound that will cause a lot of noise concerns if you are in those noise critical applications. On a side note, with the inverter compressor and digital compressor as well, there are a number of changes that are happening. I believe I briefly mentioned it, but the Department of Energy is looking at, while they will require higher minimum cooling efficiencies in that 2023 timeframe. And with these minimum efficiencies, as you can see in the screenshot below, they jump up pretty substantially compared to what used to be in the compliance date. So digital compressors will not meet those new minimum efficiencies. So as you're thinking about new projects coming out, or maybe you've always used digital, but you're curious on inverter, now is a great time to start looking at those variable speed compressors, because that is really where the direction of this type of equipment is going. And all manufacturers are going to have to switch to pretty much standardizing inverter compressors. And then here is the current compressor layout. So basically, there is one area where we already made this change. I talked about new model being the RV10. Because of the Department of Energy efficiency values coming down the pipeline in that 2023 timeframe, we didn't even want to design this unit with a digital scroll compressor. So that one will be standard and inverter compressor always, all the time. The other housings, we still have that option to select your lead compressor as digital scroll, again, giving you that good capacity control. But we do still have 5 to 70 tons as an option as well for that inverter compressor. So you can still get that option. But like I said, there's going to be a number of different changes over the next year and a half to probably eliminate digital scroll as an option for the lead compressor, moving over towards that more efficient inverter compressor option. More cooling component related items are low sound condenser fans. So that silver paddle blade type condenser fans that you see in the middle of your screen, that is going to be a common condenser fan that many manufacturers utilize in this market. What we do with the RVE product line is we use low sound condenser fans as standard on all RVE products. So any RVE condenser fan will be this low sound fan blade. I'm not sure if you are aware of the story of how this fan blade was invented, but basically they were studying various birds of prey, as you can see in that picture on the bottom left. They were actually studying the sound flight, or the flight path sound of a number of different birds of prey. They found out that the owl was the quietest bird of prey, and they took that owl wing design, that swept serrated edge blade, and they designed this condenser fan after it. So that low sound condensing fan actually reduces sound by about 5 to 8 decibels per fan. and it's actually a perceived noise reduction by about 40 to 50%. So when we're at that 60, 70 ton range, we have 8 condenser fans. 8 condenser fans being that low sound condenser fan design versus that typical paddle blade type condenser fan, that really reduces that sound. So again, a nice feature that we always have on RV/RVE, a nice thing to hold in your specifications to make sure that you're getting equal condenser fans from others as well. Sticking with the condensing section, I want to talk a little bit about EC condenser fans. A number of different options that you have on our products. First one is going to be obviously selecting none, which means all AC condensing fan motors. You can select lead, which about 43% of our orders right now are selected with lead, which means that lead condenser fan will be the EC motor. We'll modulate that one accordingly, and then we'll have AC motors staged after that. And then we do have a new option on this type of equipment where it is an all EC motor configuration, which means obviously all condensing fans will utilize those EC motors. So the big question we get is which one should be used and why? And if you're looking at none, which means all AC motors, really that's when modulating head pressure control is not required. Maybe you don't have a hot gas reheat coil, you're not as concerned about reheat capacity or maintaining head pressure, then you can likely get away with all AC motors. Lead EC motors, where that comes into play is any time that modulating head pressure control is a concern or is required. Typically, when you're modulating head pressure control, that is only done off of the lead EC motor. It's not done with all the other condensing fans. That is strictly done with that lead. And so that is where you're looking at hot gas reheat capacity concerns. So if we think about all AC motors, for example, we have part load conditions. Maybe we don't have as much heat in the system. Well, if we don't have as much heat in the system and we have all AC motors, that AC motor is going to turn all the way on and reject all that heat, even if we don't need all that heat rejected. So now because we rejected all that heat out of that condensing section, we don't have enough hot gas going back through our reheat coil. If we had the lead EC motor, now we can turn that on at minimum, turn it all the way down, and then we can reject just enough heat out of the condensing section and divert most of that heat back to that reheat coil. So during part load conditions, we can get enough capacity to get back up to that space set point that we want to see. And then moving a little further, if we go into all EC motors, that would really be for a couple different reasons. First off is if you have really sound critical applications, those additional EC condensing, or the additional condensing fans being EC motor driven, will give you the ability to modulate all of them at once, which again, obviously gives you some additional sound reduction. And then also you do get some increased energy savings for the same reason, but you do have to keep in mind the first cost of those additional EC motors is quite substantial. So that is something to keep in mind when deciding whether or not you want lead EC or all EC. So it's really determining what is the purpose and why do you need it. Remote condenser related to the cooling components that we have with the RV/RVE. This split system is a little bit different. So if you ever have to deal with split system, obviously balancing a condensing unit by a different manufacturer is pretty tough through the software as well as in the field. So what we do with our remote condenser design is we actually keep the compressors inside the unit itself, giving us the ability to pipe that compressor to the reheat coil. And then that is a nice balanced system, all from factory. And it also simplifies the field installation. So no hot gas reheat piping, no control wiring. All you really have to do is connect the liquid line and the discharge line once you get on site. You also get the single source manufacturer, which means it's a reliable and simple split system. We're able to support that product from a post-sale standpoint much easier. And you also get it factory tested. So it's going down the line together, both the actual unit as well as that remote condenser. We're going to pipe them, pump them full of refrigerant, fully test them at factory, and then obviously evacuate the system, plug them up, and send them both on their way. But this gives you the ability to know you're getting a reliable split system. We're controlling the compressor modulation. We're handling the reheat flush sequence, but you're still getting that split system design that would be required for that application. So some line lengths to be aware of with this remote condenser. Typical rise is going to be about a 2-story building, so 25 feet of rise. Doesn't matter if the condensing section is on top or basically above or below the actual RVE unit. And then the equivalent line length is about 100 feet right now. So that includes the rise, any sort of elbows or T's that you do have. And there are certain situations when we could potentially go above these line lengths. So if you do have a application that's a little bit higher or maybe a little bit longer from an equivalent line length standpoint, reach out to Holden and we'll definitely work with you on that split system application to see if there's any concern. Another unique thing I want to talk about related to cooling is design conditions. So with the design conditions, I want to specifically look at the Atlanta, Georgia market. Generally, what we're seeing is ASHRAE 90.1, the 0.4% weather bin data is generally what's used to design Doas style equipment. So obviously, there's a number of different ways you can do it. You can look at the 0.4% cooling, the 0.4% evaporation, or I would say what we see a lot from other manufacturers, or maybe what you're using right now, is 0.4% dehumidification. Obviously, Doas is meant to bring in high percentage of outside air, dehumidify that. And if you look at the dry bulbs and wet bulbs, they vary pretty drastically, specifically on the dry bulb side. And you can see the dew point vary as well. So while the 0.4% dehumidification design conditions do have the highest dew point, which you think you would want to size around, there are a couple things to think about. First one being that higher dry bulbs actually hurt compressor capacity. So if you look at the 0.4% cooling, that actually has the highest dry bulb. On top of that, the higher wet bulbs require the most cooling capacity to actually cool down to that 50, 55 degree Fahrenheit. And if you look at the evaporation, that has the highest wet bulb. So what we do is we actually use the dry bulb of the cooling day and the wet bulb of the evaporation day to properly size your system. So if you go into caps or you're working with Holden and they're in caps, the design conditions and the weather bin data that we're pulling out to standardize your selections are that dry bulb of the cooling and the wet bulb of the evaporation to make sure that we're hitting on, okay, this higher dry bulb is going to hurt compressor capacity, but we need to know about the higher wet bulb because that's going to require more capacity. Versus the dehumidification, while it does have the highest dew point, it might actually give you less capacity than you actually need for those other conditions. So now we are going to move into energy recovery and talk a little bit about some of the control strategies, some of the differences between aluminum, polymer, and things like that. So first one is going to be energy wheel comparison between the aluminum energy wheels and the polymer energy wheels. First, I will say that on our RVE equipment, we do offer both. So I'm not trying to lead you one way or the other. I'm trying to help you better understand what are some pros or cons of these different styles of energy recovery wheels. And first difference I want to look at is really just the wheel thickness. Because the aluminum transfers heat so much quicker, in order to actually recover enough energy, that wheel has to be much thicker. So the polymer wheel is about 1.5 to 3 inches thick versus the aluminum wheel is going to be 4 inches thick. So obviously much thicker, a little bit heavier. From a desiccant standpoint, so what is doing that latent energy or that humidity transfer, the aluminum wheel has a molecular sieve, and I'll talk about the application here in a couple slides. And the polymer wheel is going to have a silica gel desiccant, similar to what you'd see in those white packs in the do not eat packs in beef jerky, new pair of shoes, things like that. Effectiveness, really going to be similar across the two wheels, 70 to 80% enthalpy recovery ratio. And then from a cross leakage standpoint, looking at about 3 to 5%. Couple things related to cross leakage that I do want to touch on while we're talking about this. First one is going to be purge. We get asked a lot for purge sections, whether or not we have them, whether or not we recommend them, things like that. And really, I guess first what a purge does is it takes some more outdoor air to pressurize that purge section as you see. And what that does is it keeps that return air from actually crossing over and getting back into that supply airstream. So it does reduce that 3 to 5% to be a little bit lower, generally around that 1 to 2% range. the aluminum wheel does come standard with a purge section, but we don't really have the calculations in place, and the AHRI certifications that they report are without that purge section. So that's why technically we're still promoting that 3 to 5% cross contamination. But just so you know, that aluminum wheel does come with the purge section. And if you need the polymer wheel with the purge, we do offer that via a special design, something that you can work with Holden. But one thing I want to touch on before you utilize a purge or request a purge is the different air classifications and whether or not energy recovery can be used. And so looking at the different classes of air per ASHRAE 62.1, you can see there are 4. First one is going to be office spaces where you're likely sitting at right now, or potentially, residential type applications where you have very normal air. It's not offensive, low contaminants, 100% recirculation is allowed. Really doesn't matter about cross contamination because it's coming from a clean space. Number 2, or I should say air classification 2, would be mildly offensive smell. It's not really harmful. Think about your toilet or your bathroom type exhaust systems. Up to 10% recirculation or cross contamination is allowed. When you get into class 3, that's where up to 5% recirculation is allowed. That is where you're looking at more significant contaminants. They could be hazardous. They could smell a little bit more. So think about your nail salons, your dry cleaners, barbershops, vet offices, things like that. But up to 5% is allowed. And then class 4 is actually your hazardous, objectionable type gases, fumes, lab exhaust type systems, maybe biomedical type applications where no recirculation, absolutely 0% cross contamination is allowed. And the reason I want to walk through this is if you can think about that last slide, I said 3 to 5% cross contamination. Well, technically class 1 through 3, you're completely fine to utilize that energy recovery wheel as is without a purge. And class 4, you can't use any. So even if you did have a purge wheel and you reduced that cross contamination, you still get that 1% or 2% cross leakage. So you still could not use that in your class 4 applications. So again, while they are used, while we will offer them via special design, it's not going to help you get into an application with or without it. It's going to be the same exact class 1, 2, and 3 allowance. So hopefully that makes sense. And then for some more comparisons with the energy wheel, the aluminum wheel construction, it's a single piece. So what's nice about those polymer wheels is you get those removable segments. So from a maintenance standpoint or from a cleaning standpoint, a little easier to pull out. It's going to be lighter weight again because of that thickness. And then you're able to take out those removable segments. But cleaning wise, you can still pull out that aluminum wheel, pressure washer, get some non-corrosive detergent, wipe it down or rub it off. And then with the polymer wheels, you take out those segments and give it a little water bath with some non-corrosive detergent like Dawn Dish Soap, 409 Fantastic. Give it a little soak time, rinse it off with a low pressure hose. Once it dries out a little bit, you put that back into the unit, and then it's all good to go, all clean. What you have to be careful of throughout this cleaning process is that desiccant application. So with that aluminum wheel, I talked about the molecular sieve desiccant doing that latent transfer. That is a sprayed on application. So when you're spraying on that desiccant, if you're cleaning it and pressure washing it and rubbing it off over the course of that lifetime, you might flake off that desiccant, which means you'll lose that latent or that humidity transfer. With the polymer wheel, they actually have a permanently embedded desiccant. So you can see that picture right there. What Air Exchange does is they take those polymer strips, they apply a chemical solvent to soften that strip down, and then they provide that silica gel desiccant. Once that's applied, what happens is that polymer dries, and then it actually embeds that silica gel desiccant into that polymer material as shown in that picture. So when you're cleaning it over the lifetime of that wheel, you see a significant drop in reduction of latent energy transfer or that risk of that desiccant flaking off. So from a aluminum energy cost add, I guess I want to really quick add that this column on the right is wheel price only. So it's not the unit itself add. It's not saying with the aluminum energy wheel, it's going to be an 86% cost add to utilize those aluminum energy wheels, but the wheel specifically that's going in there will be an 86% or 41% cost add, depending on the housing size. And generally the wheels are about 5 to 10% of the cost of the overall unit itself. So it does add up. Reason being is, and we'll touch on frost control, but aluminum wheels, we require that VFD to be standard on the aluminum wheel for frost control. So it's a modulating wheel frost condition just because there's more risk with aluminum wheels getting damaged during frost conditions compared to polymer wheels. Also, they get a little heavier, so there's risk on belts and motors becoming less useful over the lifetime. So that is why we have that. So if you were to add a VFD on the polymer wheel as well, these differences in price would also shrink because then they would be more apples to apples. But other thing to point out is the maximum CFM between the two also changes. So you can see in each housing, except the 85 housing, the polymer wheel moves a little bit more airflow from an overall housing standpoint. So we do go up to 14,800 on the aluminum, up to 18,000 on the polymer type energy recovery wheels. So some energy recovery wheel control options. I want to first touch on frost control. So a couple different options that you can have. First one is going to be the electric preheater. So this basically, it is what it says. It preheats the incoming air with an electric heater so that we avoid any sort of cold air moving across that wheel and freezing that wheel. Timed exhaust, really what it does is it cycles the supply fan on and off, which that allows as the wheel is rotating, it just allows that warm exhaust air to melt any sort of frost condition that there is. And then modulating wheel uses a VFD, reduces that rotational speed so it spends more time in that return airstream to again melt those frost conditions. Biggest thing to know in relation to frost control is it really does depend on both your application and where you're located. So as you can see in the Georgia market, generally no frost control really is needed because you don't get cold enough where there's going to be a concern. As you can get to the Midwest and the central United States, now timed exhaust or modulated wheel might be okay, but when you get really to the northern part of the country, that is where we're going to really require electric preheater or recommend preheaters because there's a lot larger risk for frost buildup. Now, with that being said, it obviously does depend on your application as well. There's a big difference between a space that is very dry, maybe 35%, 30% relative humidity coming back, versus a locker room type application where maybe you have 60% relative humidity coming back. There's going to be a lot more buildup of moisture on that wheel. So now we might change the frost control recommendations that we make. So this map shows one thing, but obviously the table on the right, it does really depend on your application as well. And then from an economizer standpoint, really looking at two different options. You're going to stop the wheel or you're going to modulate the wheel. And when you stop the wheel, it is doing what it says, is the energy wheel is de-energized and the outdoor air is just brought in through the wheel. Obviously, no energy recovery is taking place. And then modulating wheel, we're just reducing that VFD or that speed again to maximize the free cooling that we get, which is reducing that wheel effectiveness. So those are really the options that you'll see on this type of equipment. The third option that you might be familiar with, maybe you prefer, or maybe you see in the market, is wheel bypass. And we do get this request, we do see it, but I want to break that down a little bit and give you our stance on and when you would see it on the RVE product lines. But understanding this, first off, I want to give an example of a classroom that is 6,000 CFM units. And in that 6,000 CFM Doas unit, you have two energy recovery options. You have a 52-inch wheel with bypass dampers for economizer, or you have a 58-inch wheel without bypass dampers. So obviously, without the bypass dampers, we have room to expand that energy recovery wheel. So looking at the economics of these two different wheels, without bypass, you see an enthalpy effectiveness of about 65%. Compared to the 52-inch wheel, even if the bypass is closed and all of that air is going through the energy recovery wheel, because it's a smaller wheel, the enthalpy effectiveness actually goes down a little bit. So it's 63%, not a huge reduction, but still would definitely be able to potentially downsize your cooling and heating downstream, or you would save energy on your capacities required when using energy recovery. Another thing to look at is pressure drop. So a lot of the conversations around wheel bypass is that during economizer mode, you get a reduction in pressure drop during those modes or during those times. But with the larger wheel, you actually get a lower pressure drop during normal operation because your wheel is larger. So it's about 0.76 in this case versus 0.9 with that 52-inch wheel with bypass closed. So looking at if you had a 5 days a week, 12-hour a day application versus 24/7, with the 58-inch wheel, this is specifically looking at fan energy savings. So you can see the cost that it would take to operate that fan. It's about $156 reduction in the first situation, and if it's 24/7, about $400 reduction from fan energy operation per year. Okay, now what I want to look at is how often would basically any time to save energy, and the reason you want wheel bypass is during economizer, right? So when the wheel bypass is open. But how often would it need to be open to actually make up those energy savings during normal operation? And our study actually showed about 40% of the time. And that assumes a 50% reduction in pressure drop with that bypass open, which is actually pretty aggressive. So it's likely not going to be half of the pressure drop. But in this situation, that's what we looked at. But you can see 40% of the time, and generally, especially in the Southeast, you're not in economizer 40% of the time. So maybe certain applications, maybe on the West Coast, it makes sense if you have a lot more hours worth of economizer. But if you're sitting around that 5, 10, 15% time frame of economizer, it makes more sense to actually expand the energy recovery wheel to get as large as possible, increase your effectiveness, reduce your pressure drop during normal operation, and obviously save that fan energy during normal operation versus during economizer. So hopefully that situation makes sense, but that's where our stance is in a Doas equipment with wheel bypass dampers. Now, where does it make sense to use wheel bypass? So really any partial recirc applications where you have lower outdoor air percentage. So obviously you can still have lower outdoor air percentages and use energy recovery. In this example, we're looking at a gymnasium. Let's say we have 12,000 CFM of supply, 3,000 CFM of outdoor air, right? So the energy wheel is typically only needing to be sized for 3,000 CFM of that design outdoor air. But when we go into economizer, we're ramping up that outdoor air damper and bringing in more outdoor air, potentially up to 12,000 CFM. Well, the energy wheel is only sized for 3,000. So if we put 12,000 CFM through that energy wheel, there's a good chance that that wheel is going to blow apart. So we don't want to damage that energy wheel. So that is where wheel bypass makes sense, right? We put the energy wheel bypass in there. During economizers, we'll open it up because that wheel is only sized for 3,000 CFM, and then we'll bypass the rest. But for the Doas, the wheel's already sized appropriately. It's already sized for all the possible outdoor air that could come in. So we don't want to undersize the wheel to fit bypass dampers in. So hopefully that clears up where you would see wheel bypass from the RVE product line and maybe when you would want to specify it. One other concern not related to economizer is in certain manufacturers, what we see is bypass dampers do only reduce wheel pressure drop by 25 to 50%. But the big one is this allows air to short circuit the energy wheel during normal operation. And what I mean is they have to undersize the energy wheel so they don't have to expand their housing. And in order to move the overall supply airflow that they want, they actually have to bypass some outdoor air during normal operation because that specific energy wheel in this case is only sized for a maximum of 5,000 CFM. So even if they're not in economizer, they're only moving 5,000 CFM through the energy wheel and bypassing that other really high temperature, really high humidity outdoor air around. So instead of all of that air leaving the energy wheel at this 83 degrees that you see on there, now it's actually mixing prior to the cooling coil at 86 degree dry bulb, 71 degree wet bulb. So your cooling has to be increased downstream. Again, so during normal operation, that's going to reduce the effectiveness. It might put you in harm of not meeting that 50% effectiveness from a code standpoint. So always things you want to consider when looking at wheel bypass. Now I want to move into more the controls and the commissioning side of things. And first one is going to be with our factory controller. So really easy commissioning with our factory controller. We have a standalone Correlate microprocessor with optional BMS integration. And what we do is we utilize a controller from Correlate, and all it is a skeleton. And I'm sure some of you are familiar with it, but what we do is we take that skeleton from Correlate and we download all of our proprietary knowledge, the logic and the sequencing that we've built over the last 20 to 25 years of doing this type of equipment. And then it's factory programmed exactly how it was ordered. So for example, if it was ordered with duct pressure supply fan control for a multi-zone VAV type application, it will come programmed with duct pressure supply fan control. So all you have to do is tie in that duct pressure sensor in the field and then set that appropriate pressure you want to maintain. Let's just say down the road, all of a sudden something happened and you want to change it to constant volume supply fan control. Instead of getting a big factory update or program update that you need to do on that controller, all you have to do is get into that control screen, change that supply fan from duct pressure over to constant volume, and then that screen will come to the surface. So all of that logic is built in that controller. It's just really what's at the surface configured at that time. Another nice thing is we have the built-in furnace commissioning. So as you have startup techs or contractors going out on that roof, commissioning this equipment, we have a really nice furnace commissioning menu that is a step-by-step guide to make sure that they're doing the right things to commission that furnace and to make it easier at that time. So it's going to say, you know, is this gas LP or natural gas? Do you have your manometer? Do you have it hooked up to this valve and this valve? And it's going to walk you through step by step. We're also looking at adding certain commissioning sequences for cooling and maybe energy recovery or fans in this type of logic as well, where there's going to be continual layout screens like that for different commissioning sequences. And we do have the web user interface, which because of time, I'll pass over that right now. If you have any questions or if we have time at the end, I'll go into the web user interface. But really what that is it's a way to remotely monitor via a web UI if you're connected to the building network. And if you have any questions, reach out to the Holden guys. They'll definitely walk you through that, or you can ask for some sort of webinar in the future as well. But related to controls, I want to touch on some set point ranges that we have on our controllers, specifically related to more DX situations. So first off, I want to talk about the cold coil. The cold coil can be set anywhere from 46 degrees up to 80 degrees. So I believe there was one question about low dew point type applications. The way that we are configured and set up and based on our factory testing, 46 degrees off that cooling coil is the minimum that we will go during dehumidification. Now, if we're in cooling only, or if we're in that type of situation and it's just cooling where we're not needing to drive that to a low dew point, the minimum overall supply discharge temp that you can get is 50 degrees, and then the maximum would be 100 degrees. So that is the range that you're seeing from an overall supply discharge set point. And then from a cooling ambient lockout, 55 degrees will be, if we think back to those condenser fans, if it's all AC, so if you select no EC condenser fans, 55 degrees is really going to be that ambient lockout. Now, if you have that lead EC or all EC motor selected on the condensing fans, currently right now we can go down to 35 degrees if that's the case. If you have certain applications where, in Georgia, you probably won't need to go much lower than that. But if you're working on applications where maybe it's somewhere else that they need low ambient cooling, we can always look at that via special design. But again, work with Holden, they'll work with us, and we can look internally with our performance on the refrigeration side of things. And then another interesting fact I wanted to make aware is dehumidification enabled. So obviously when we go into dehumidification mode, that is where we're looking at that cold coil set point, driving to those lower dew points and stripping off all the moisture that we can. So a couple enable set points from factory, the standard sequence will be whatever that cold coil set point is, plus an offset of 10 degrees from the outdoor air temp. That is when we're going to enable dehumidification. So for example, if it's a 55 degree cold coil set point, anytime that it is 65 degrees or warmer outside, that is when we're going to enable dehumidification to strip that moisture off. That is adjustable, that offset. So if you want it to be 5 degrees, if you wanted it to be 15 degrees, whatever that may be, that is an adjustable offset. If you didn't like enabling dehumidification based off of that sequence, you can look at the indoor relative humidity. You can look at the indoor dew point if you wanted to and had the appropriate sensors, or even the outdoor dew point at that time as well. So a lot of different ways to look at when we want to enable dehumidification. And then there's also additional options to utilize a combination of the above, where it might be inside dew point or inside relative humidity, things like that. Moving on to heat cool only control. So obviously not necessarily full factory controls, and where we generally see this being very common is in school or education type situations. So a lot of the times we see school districts or maybe counties that prefer their third-party controller or their own controls logic that is handling all the equipment on the building. So what we do with this is we have a terminal strip that we allow that third-party controller to be tied into. And then from that terminal strip, there's two different things that happen. If it is non-tempering components like energy wheels, fans, dampers, things like that, there's direct control over that with that third-party controller. Now, if it is things related to refrigeration and heating, we have what is called our heat cool only controller that is essentially taking inputs from that third-party controller and then modulating the cooling and the heating accordingly to basically maintain set point, stay within the compressor envelope, stay within the safety factors, things like that. But with that, we're still accepting inputs from that third-party controller. So it's the third-party controller is still telling us when to heat, when to cool, when to dehumidify. It's telling us the set point they want for heating or dehumidification or cooling. And then we're taking that information that we get from that terminal strip, and then we're applying that to our logic to make sure that we're operating that cooling and heating accordingly. So this is an example of some points that you would see. As an example, there's some different analog commands, digital commands, different statuses that we may provide from our controller back or from relays back to the terminal strip that you can read with that third-party controller. Obviously, there's a lot more to this list. And if you have any questions, again, reach out to Holden. We can make sure you have this list. But I will say this is a great option for any time you want a third-party controller, but it's still allowing us to make sure that we're in safe operating ranges with all of our cooling and heating. As a side note, talked about the Department of Energy and the efficiency requirements. With inverter compressors, we are the only manufacturer that really allows this terminal strip type control setup. So inverter compressors are a whole different animal when it comes to controlling them and keeping them within the compressor envelope and operating that VFD. So manufacturers won't be able to provide terminal strip type controls or those full-blown terminal strip type controls right now. So as you're making the change over to variable speed or inverter compressors, keep in mind that this is really the only terminal strip type control on the market that allows you to utilize that with those variable speed compressors. So I want to end here with some RVE advantages, just where we're at in the market in relative terms to what we offer on our equipment. And first one's obviously construction and coating, and some of this might be repeats for you guys, but hopefully you're starting to see that in the field if you're utilizing our equipment. But with our RVE housings, it's double wall construction, and we have 2-inch R13 injected foam. And I want to make the injected part clear, because a lot of the times that we're seeing other competitors utilize 2-inch R13 foams, they're using panel boards, which means there's a lot of gaps and not enough thermal breaks in that type of panel or in that type of foam construction. So we standardly inject that R13 foam in the base as well as the unit. So what's nice about the base is it reduces both noise transmission into the building as well as some additional thermal resistance that you're going to lose, especially if you have an uninsulated curb, maybe it's pad mounted, things like that. It does reduce that noise, like I said, especially with digital scroll type compressors, if you've ever heard those noise concerns, because we have that 2-inch R13 base and we have the compressors elevated on an elevated shelf in an insulated cabinet, definitely don't get that concern from a noise standpoint either. Other manufacturers, what you're seeing is, again, 2-inch R13 foam, more so foam boards. But from a base insulation standpoint, standardly, they're not going to offer base insulation. And then if they do, you're generally going to see a 1/2 inch or maybe up to 1 inch of that base insulation. So just keep in mind that we have that 2-inch base insulation as well. And then from a coating standpoint, Our standard coating is 2,500 hour salt spray rating. That's that nice permatector coating. Again, standard on all RVEs. If you do have those situations where you need to increase that salt spray rating, we go up to 5,000 hours with our high pro poly coating. We can also do some color match options on that one as well. Generally, what you're seeing from other manufacturers is 150 to around 1,000 hour salt spray rating as standard. Another nice thing is radiated sound. So again, talking about sound ordinances, there's a couple of things I mentioned that we do, like the low sound condenser fans, the base insulation, things like that. But with the radiated sound, we provide AMCA tested sound information in our submittal. So we have 5 planes of information for you guys in the submittal package. You can see in the picture, that's an example of how we test that unit. If you've ever been up to Greenheck, you might have seen our Innovation Center, which is amazing. And what's nice about the Innovation Center is it is built on 1,000 different isolators so that that actual innovation chamber, or that sound chamber, is isolated from the rest of the equipment. So it truly does give us accurate seismic calculations as well as sound ratings that you might see. An example that you might see from other manufacturers is generally sound power levels are given for informational purposes only, or maybe they're informational and they're not guaranteed. And the concern with that is if you're dealing with a sound tight application, we want to make sure that what we're providing from a sound standpoint gives you the peace of mind that that's how it's going to sound when it's on site. So the radiated sound, we're testing it at full condenser fans, full compressors, full heating, things like that to make sure you know how it's going to operate. We actually had a group out of Boston, Massachusetts, a group of acoustical engineers test our equipment when it was on site, and they tested the same exact information that we had in our submittal. So again, proving that what we're putting out there is accurate, and we do pride ourselves on putting out the most accurate information we can for you guys as the customers. Another nice advantage we have on the RVE and RV product line is horizontal connections. So with all the redesigns that we did and the new housings we rolled out, now from 3 to 70 tons on all the housings, you should be able to get horizontal connections. What's nice about that is it eliminates the need for a tall, costly plenum curb. So if you want to mount it on a smaller curb, if you want to mount it on a pad or indoors, gives you the ability to do that with those full horizontal connections, which means it doesn't have to look like this, right? We want to reduce the installation time and cost that you guys are seeing out there. Plenum curb adds about $3,500 over a standard curb. And then if it requires a service platform because it's too high, that's about another $4,000. So definitely want to utilize it to your advantage with those full horizontal connections in the RVE product line. And then lastly here, want to touch on RTU versus Doas. That is a big question right now, especially in this market. Some big differences between the two is obviously your traditional rooftop unit, generally looking at 20 to 30% outdoor air maximum. When we talk about Doas units or think about the RVE product line, generally trying to size for 20 up to 100% of outside air. Are there times that we can go below 20%? Absolutely, depending on the situation there. But generally, that's what you're looking at, 20 to 100%. With RTUs, more so staged on off or potentially 3-stage compressors versus true modulating compressors with that digital and inverter technology on these Doas type equipment. Belt-driven blowers on the RTU versus the direct drive plenum fans handling higher statics in the Doas units. And then from a construction standpoint, seeing foil face insulation, maybe single panel construction with less thermal breaks, less thermal resistance compared to the double-walled 2-inch R13 injected foam that you're seeing on the Doas side of things. So when to use Doas? Well, first off, if it's higher percentage of outdoor air required, so anytime that you're really looking above 20% outside air, that's when you're going to want to start looking at the RVE product line or Doas type units. Another one that we see is when high amount of outdoor CFM is required. Maybe it's not necessarily above 20 or above 30 or above 40%, but what happens when there's a high amount of outdoor CFM in general required, so high occupancy food halls, or maybe you're just looking at with the pandemic and with all the illness out there, you just want to utilize more outdoor CFM, even if it's way over the minimum required. When that's the case, if RTUs are only designed for 20% outside air, Now you have to start adding 2, 3, 4, 5 rooftop units just to be able to handle the outdoor CFM that you want to use, versus 1 or 2 Doas units that could handle that CFM in a much smaller housing, which with obviously reduced installation time. So as you're thinking about bringing in more fresh air during these tough times and during the pandemics and epidemics and things like that, think about looking at Doas, even if it's only around that 20 to 30% outdoor air, because you're going to get smaller footprints and you're going to get less units. Tight temperature control, if that is required, you're looking at, again, the modulating compressors, the much more robust controls, the better insulation. That's when you're going to look at Doas. So if you have those applications where you really need to maintain a certain leaving dew point, or you need to maintain a tight temperature control without cycling as much, that's when you're going to want to look at more of the RVE equipment. And then lastly, energy savings during night setback. And it's really due to the superior controls and modulating compressors, things like that, where during night setback, we still want to maintain that, temperature and humidity in the space. We don't want stick building syndrome. We don't want it to go unconditioned during those setback hours. So what we do is, with our control strategy, we can still have different unoccupied set points that might be a little bit higher from a temperature and humidity standpoint, but we'll read those and we'll control our compressors and our heating the same way. We'll stage our fans on just to move enough air to get that back down to set point, which means we're saving energy in the long run. So those are the general themes when you're going to want to look at that RTU versus that Doas, and make that jump over to the RVE product line. But other than that, I guess a lot of information that was thrown at you here in about 58 minutes. Appreciate your time. Definitely going to want to answer some questions if you guys have them.
Yeah, so there's a couple questions that have come up. Does the part load on digital scroll correlate to less amps?
So that one is, it's tricky. So from an amperage standpoint, it really does depend on the overall compressor size. So what we were able to do is we're actually able to overspeed compressors with inverter compressors. So we might actually be able to get smaller compressors inside the housings compared to digital, and actually overspeed them with the VFD, versus digital, we're really limited just to that 100%. So in that case, it actually could reduce in lower amperage compared to the digital scroll. Now, from an MCA MOP standpoint, what's tough is sometimes our technology or the compressors are sized with larger VFDs than are necessarily required. And what happens is, per code, you actually have to look at either whatever's larger, either the overall amperage pull or 65% of the VFD amperage rating. And if that VFD is oversized, you might see the MCA be larger with an inverter compressor compared to the digital scroll compressor, because we had to size it off of that 65%. So if you ever see those questions, definitely reach out. We can potentially look at some energy or some operational savings that you'll get. But it really does depend on the situation, but that's a good question.
The next one was, what is the cost difference? This was referring to the aluminum and polymer wheels. I think this was right before you hit that slide that was, I think, 41%, 86%, just for the wheel.
And again, it varies. There's ranges with those. Obviously the best thing to do would be pick an aluminum and a polymer, both in caps. If you want true apples to apples, you would have to select the polymer wheel with the VFD as well for frost control or economizer. But I would say, from an operational standpoint and from an energy savings as well, the polymer wheel will be cheaper in the long run, and the upfront cost, again, is that 40 to 80% compared to that aluminum wheel. So definitely a lot of good reasons to utilize polymer wheels.
The next one, factory setups for DCV, basically on the factory controller.
Yeah, that's a really good question. So there's a number of different things that we'll do with demand control ventilation. Obviously, most common, looking at the CO2 in the space or the duct. If it's 100% outdoor air, you can certainly utilize a CO2 sensor from factory, where we're going to obviously modulate that supply fan up and down based on that CO2 reading in the parts per million from the space. And then if it's partial recirc, you can do the same thing with the dampers. So obviously, whatever your supply fan's doing at that time, we're going to adjust our dampers accordingly to bring in more or less outside air. You can also utilize it through BMS. So if you're using BMS integration to control supply fan or damper control, maybe you have a certain CO2 sensor that you want to read from the head end or from your building management system. You can also write that parts per million value to us and we can control it accordingly. Or you can actually specifically write that supply fan speed or that damper set point that you want as well. So from that standpoint, that's generally what you're seeing. And then also single zone VAV is another type of demand option that we do have. So looking at that space temperature to adjust that supply fan up and down to make sure we're meeting that space set point as quickly as possible.
And that is that built in directly to the controller? Is that standard programmed already in?
So if it's selected, it is programmed already from factory, no matter how it's selected. Again, if it's not configured and all of a sudden it gets on field and you wanted it, maybe you ordered it for constant volume, you wanted the BMS to write that set point, but all of a sudden something happened and you didn't have the ability to do that. You work with Holden, all we have to do is get a CO2 sensor out there, or maybe you provide your own. And then what happens is you tie it in, you work with us, we have a dedicated input for, let's just say, supply fan control or damper control. You land it at that input, and then we just get in there and change one screen. That's supply fan control from constant volume over to CO2 control, and then that is how it's set up. So really not that big of change if it's in the factory either, which is what's nice about a controller. It's not going to require a big program update.
This question kind of goes back to the digital scroll question that was just up. Did you say that you were the only manufacturer that was compatible with digital scroll compressors with respect to control systems? Did I misread your statement? Would this be a chiller compressor?
So no, basically when I was going with the only manufacturer related to controls and compressors is more of that heat cool only or that terminal strip type option with inverter compressors. So digital scroll compressors, you'll see a lot of manufacturers utilize terminal strip or third-party controls, allowing basically a third-party controller to take direct control over those compressors. But with inverter compressors, you can't give full control to the field just because there's so much more that goes into controlling it and keeping it within safe operating range. So we're the only manufacturer as of right now that has the allowance for some sort of third-party type control while still utilizing an inverter compressor.